السلام عليكم طلاب. في هذا الفيديو سوف نتكلم عن الأوبتيكال أكتيفيتي، الفعالية البصرية. راح نسمع هذا الفيديو وأثناء السماع راح نشرح الأشياء المهمة في هذا الفيديو.
In this video, we're going to talk about optical activity. We're going to discuss whether a molecule is optically active or optically inactive. And we're going to talk about specific rotation and how to get it from observed rotation. We're going to discuss terms such as optical purity and enantiomeric excess. So let's begin our discussion with enantiomers.
لنبدأ في هذا الفيديو للانتايمرز المتمارئات.
Enantiomers have a chiral carbon.
يحتوي على كربون كيرالية.
Is basically a carbon with 4 different groups attached to it.
كربون كيرالية تحتوي على 4 مجاميع
The first group
مختلفة.
that I drew was a methyl group. The second group was a hydrogen. The third was the carboxylic acid functional group. And the last
لاحظ هاي الجزيئة هي جزيئة كيرالية تحتوي على مركز كيرالي أو ذرة كربون كيرالية مرتبطة بها 4 مجاميع مختلفة. إذن هاي الجزيئة كان exist as enantiomers. راح نرسم المتمارئ الآخر.
To draw the enantiomer of this molecule, we simply need to draw its mirror image. So we're going to
راح نرسم صورة المرآة لهذا المركب. هذول they are not superposable mirror image of each other. يعني الانتايمرز are not superposable mirror image of each other. لهما نفس الصورة ولكن لا يتطابقان، مثل ما شرحنا اليد اليسرى عندما نضعها أمام المرآة تعطينا اليد اليمنى ولكن غير متطابقين، اليسرى مع اليمنى غير متطابقين. كذلك هذا المركب صورة مرآته هذا ولكن non-superposable mirror image.
It draws reflection across that vertical dash line. Here, the OH group is pointing towards the left. Now, it's going to be pointing towards the right. Now, let's assign RNS configuration to each chiral center. To do that, using the Kahn-Ingold-Prelow process, we need to rank the priorities based on atomic number. Oxygen has the highest atomic number. Next is carbon. Here we have 2 carbon atoms, but this is an oxygen versus a hydrogen, so the oxygen will win over the hydrogen. This will be group number 2, 3, and H is always 4. So counting from 1 to 2 to 3, this is going to be the S isomer because we're rotating it in the counterclockwise direction. Now for the molecule on the right, this is going to be group number 1, number 2, 3, H is 4. So if we count it from 1 to 2 to 3, ignoring 4, we can see that we're rotating it in the clockwise direction, giving us the R isomer. So the molecule on the left is called.
احنا هنا بالنسبة لهاي الجزيئة أو المتمارئات عينا الأس والآر، اعتماد على الأولوية واعتماد على الأوتوميك نمبر اللي هو العدد الذري، ومثل ما شرحناه بالفيديو السابق.
Called S lactic acid. Whereas the molecule on the right, this is called R lactic acid. These 2 enantiomers, which are mirror images of each other, they have different optical properties, but they have the same physical properties. So enantiomers have same physical properties like boiling point, melting point, density, solubility. It's the same for these 2 isomers. However, their optical properties are different. the way they rotate plane polarized light is not the same. It turns out that
إذن هذول المتمارئات have the same boiling point and melting point ولكن يختلفون مثل ما تعرفون في خاصية واحدة اللي هي دوران مستوى الضوء المستقطب. واحد من عندهم يدور نحو اليمين أو مع عقرب الساعة والآخر عكس عقرب الساعة وبنفس الدجري نفس الدرجة. فهم يختلفون فقط في خاصية فيزيائية واحدة اللي هي دوران مستوى الضوء المستقطب.
that the S isomer rotates light towards the right, and the R isomer rotates plane polarized light towards the left. Now, when it rotates light towards the right, there's a positive sign that is associated with that. When it rotates light towards the left, there's a negative sign associated with that.
إذا هذا المركب الأس لاكتيك أسيد دور مستوى الضوء المستقطب نحو اليمين أو مع عقرب الساعة أعطينا إشارة موجب، والآخر دور مستوى الضوء المستقطب نحو اليسار أو عكس عقرب الساعة وأعطينا إشارة السالب.
So this is known as the D isomer. The D standing for dextro-rotatorium. The prefix dextro tells us that it's rotating light towards the right.
A 22-year-old with 28 days of AI training is currently outbidding you for your dream job.
They're not more qualified, they're just faster. Don't watch.
The negative sign is associated with the L isomer, which is known as levo-rotatorium. Hopefully I said that right. But it rotates plane polarized light towards the left. Now, the S isomer is not always associated with the D isomer. The S can rotate light towards the right, or it can do it towards the left. So S is not
طلاب
always
ملاحظة
associated with.
هنا احنا دوران مستوى الضوء المستقطب نحو اليمين او اليسار ما تعتمد على الاس والار. هذا الدوران يعتمد على طريقة العمل على التجربة نفسها. الاس والار هاي تسمية ضمن قواعد معينة، والموجب والسالب يعني دوران مستوى الضوء المستقطب نحو اليمين او اليسار تعتمد على التجربة وعلى نفس المتمارئ. يعني ما لهم مرات نلقى اس سالب ومرات نلقى موجب، مرات نلقى ار سالب وفي بعض الأحيان موجب.
The positive dextro-rotatory molecule. So sometimes the S isomer could be positive, other times it could be negative, depending on the molecule you're dealing with. Same thing for R. The R isomer could be positive, or can rotate light towards the left. So you can't really determine if it's positive or negative just by looking at the configuration of the chiral center. So just because you have the S isomer doesn't mean you have the D isomer, the L isomer. They're not associated. The S and R tells you the configuration at the chiral center, but the plus or minus tells you how that particular isomer rotates plane polarized light. So S doesn't always rotate plane polarized light to the right. For some molecules, it will rotate it towards the left, which it varies from molecule to molecule. So I want to make sure you get this because this is a typical test question. So remember, S can be positive or it could be negative depending on the molecule. Sometimes it will rotate light towards the right, and other times the S isomer will rotate light towards the left. Same thing for R. For some R molecules, it will rotate light towards the right, and for other R isomers, it can rotate light towards the left. So R doesn't always mean that it's positive, nor does it always mean that it's negative. It varies. They're not direct. There's no direct association between R and plus or R and minus. Now let's say if we have a light bulb. A light bulb, through the process of incandescence emits light in all directions.
الضوء الاعتيادي
So we're going to have light
يمرر
along
الضوء إلى جميع الاتجاهات.
the vertical axis, light along the horizontal axis, and just going in all directions. This is normal light. Now, if we pass through normal light, if we take normal light and pass it through, let's say like a polarizer, the polarizer is going to act as a filter.
البولارايزر أو اللي هي العدسة بولارايزر هي مثل فلتر.
Most of the light is going to absorb, but it's going to
معظم
allow
الضوء سوف يمتص.
a certain type of light that is in the direction of the polarizer to pass through. So in this case, only the vertical portion of light will pass through. So this is known as plane polarized light.
هذا يسمى
It's been
plain
polarized
polarized
by
light.
the
مستوى
polarizer.
الضوء المستقطب.
Now what we're going to do is we're going to pass this through a sample tube.
هاي الخلية اللي نضع بها السامبل.
Now let's say this sample tube contains an achiral molecule.
في
achiral
حالة إذا
does
كانت
not rotate.
في حالة الجزيء إذا كانت غير كيرالية ما يدور مستوى الضوء المستقطب لا نحو اليمين ولا نحو اليسار، ويبقى مستوى الضوء ثابت على الصفر يعني.
Plane polarized light. So as a result, as light passes through the tube, the molecules in this sample tube will have no effect on the plane polarized light. So the light will emerge the sample tube without any rotation. So there won't be no rotating this plane polarized light if you have achiral molecules in the sample tube.
في حالة وجود جزيئة غير كيرالية بالتوب ما راح يدور مستوى الضوء المستقطب، وليس له أي تأثير على الضوء المستقطب لكون هاي الجزيئية هي غير فعالة بصريا. الجزيئات الغير كيرالية هي غير فعالة بصريا.
Now let's see what happens if we put a chiral molecule in a sample tube. So we're going to follow the same process. We're going to take light traveling in all directions. We're going to pass it through a polarizer. And we're going to obtain plane polarized light. We're going to filter out all of the unwanted light traveling in different directions, but the light that is in line with the polarizer, that's going to come through. Now, just like before, we're going to pass it through a sample tube. This time, inside the sample tube, we're going to have chiral molecules as opposed to achiral
وضعنا
molecules.
في الخلية جزيئة كيرالية.
So if we
chiral
have a
molecule.
chiral molecule, let's say like one form of the enantiomer, let's say the S enantiomer, this is going to rotate the plane polarized light. So as the light passes through, it will begin to change direction.
يعني شنو
And so
يحصل
when it
بما
emerged
أنه هي جزيئة
from the sample
كيرالية سوف
it's not-
تعمل على دوران مستوى الضوء المستقطب.
Not going to be at the same angle in which it was. Notice that it rotated by some degree. Maybe it rotated 15 degrees or 20 degrees, but there was some rotation here. So what you need to know is that chiral molecules, they are optically active.
لذلك يسمى الجزيئات الكيرالية هي فعالة optical reactive، هي فعالة بصريا. لماذا سميت بفعالة بصريا؟ لكون تدور مستوى الضوء المستقطب أما نحو اليمين أو نحو اليسار.
They show optical activity. They can rotate plane polarized light. Achiral molecules are optically inactive. They do not rotate plane polarized light. So how can we determine if a molecule is optically active or optically inactive? Let's work on some examples. So I'm going to draw a few molecules, and I want you to determine whether it's optically active or optically inactive. Feel free to pause the video as you work on these examples.
If your legs feel heavy and swollen by evening, you need to do these 5 exercises for 7 minutes daily.
جزيئات أريد نعرف أي من هذه الجزيئات هي active فعالة بصريا أو غير فعالة بصريا.
So this one's going to be trans instead of cis. So which of these molecules are optically active and which ones are optically inactive? In order to determine the answer, we just got to determine which one is chiral and which one is achiral. Let's start with this one. If you have a molecule with no chiral centers, that is with no carbon atoms that don't have 4 groups, that molecule is going to be achiral.
لنبدأ في هذه الجزيئة اللي هي واحدة اللي هي نورمال هكسان. طبعا هاي الجزيئة ليس لها مركز كيرالي أو ذرة كربون كيرالية، إذن هاي الجزيئة هي غير كيرالية، لذلك هي is inactive optically inactive غير فعالة بصريا، يكون هي جزيئة غير كيرالية لا تحتوي على مركز كيرالي.
Every carbon atom, there's no carbon atom in hexane that has 4 different groups, so there are no chiral centers, which means the entire molecule is achiral. And if the molecule is achiral, then this molecule is said to be optically inactive. It will not rotate plane polarized light.
إذن الفعالية البصرية لها علاقة إذا كانت الجزيئة كيرالية أو غير كيرالية. فبما أنه هاي الجزيئة غير كيرالية، فإذن هاي الجزيئة أيضا هي غير فعالة بصريا.
Now, when you have a molecule that have 1 chiral center, like this one, that carbon has 4 different groups, that molecule is going to be chiral overall.
هذه الجزيئة لها مركز كيرالي واحد، والمركز الكيرالي مثل ما شرحناه اللي هو ذرة كربون كيرالية مرتبطة بها 4 مجاميع مختلفة. إذن هاي الجزيئة هي جزيئة كيرالية،
So if it's chiral, that means that it's going to be optically
إذا
active.
كانت جزيئة كيرالية معناها هي can be optically active، ممكن أن تكون فعالة بصريا.
This will rotate plane polarized light. Now, when you have 2 chiral centers, like this one, you need to look at symmetry.
هنا عندنا ليس مركز كيرالي واحد، مركزين، لازم نلاحظ التماثل أو التناظر، مستوى التماثل أو التناظر plane of symmetry. فنلاحظ هنا بما أنه اثنيناتهم CR on the same side في نفس الجهة، فهاي الجزيئة لها مستوى تماثل وهي جزيئة غير كيرالية، وبذلك فهي غير فعالة بصريا.
If there is a plane of symmetry, what you have is a meso compound, and so it's going to be achiral.
هذا نسميه ميزو كومباوند، مركب ميزو كومباوند لها مستوى تماثل.
Which means it's optically inactive. Here's another example. Here we have a molecule with 2 chiral centers, and there's a plane of symmetry. So this molecule is going to be achiral.
كذلك هذه الجزيئة لها مستوى تماثل وهي جزيئة غير كيرالية، ولذلك فهي غير فعالة بصريا. نلاحظ ذرتي الفلور اثنيناتهم واقعين في الأمام، إذا معناها لهم مستوى تناظر أو تماثل. إذا هاي الجزيئة هي ميسو كومباوند وهي جزيئة غير كيرالية، لذلك هي غير فعالة بصريا.
Now for this one, here we have two chiral centers.
نلاحظ هنا هذا المركب لا يحتوي على مستوى تماثل. ليش؟ يكون هنا عندنا مجاميع ال OH، واحد من عندها في الأمام والآخر في الخلف. لذلك هذه الجزيئة هي جزيئة كيرالية وتكون فعالة بصريا.
You don't have a plane of symmetry. The OH is on the front. Here, this one is on the back. That's going into the page. So this is a chiral molecule. And so this molecule will show optical activity. It will be optically active. Now for the last one, this is not a chiral center. We have a hydroxyl group.
نلاحظ هنا هذا المركب لا يحتوي على مركز كيرالي. يكون عندنا المركز الكيرالي لازم 4 مجاميع مختلفة. هاي الجهة هي مشابهة للجهة الأخرى. لذلك هاي الجزيئة هي جزيئة غير كيرالية وليس فعالة بصريا.
There's a hydrogen, but notice that the left side is the same as the right side. So there are no chiral centers for that molecule. Therefore, this is an achiral molecule, which means it's optically inactive. It will not rotate plane polarized light. Now let's talk about some formulas that you need to be aware of. The specific rotation is equal.
هاي تسمى specific rotation، الدوران النوعي.
To the observed rotation, represented by the symbol alpha, divided by the path length times the concentration. So alpha without the brackets is the observed rotation, and it's measured. It's an angle measured in degrees. The same is true for the specific rotation, which is in a bracket. Which is typically in grams per milliliter. Sometimes it might be represented in literature as grams per 100 milliliters.
تركيز غرام لكل مليلتر أو غرام لكل 100 مليلتر.
Is the length of the sample tube. So earlier we drew the sample tube like this. So L is the path length, or the length of the sample tube.
هذا طول السير
That's
أو
how far
الطول
light has to travel
المستخدم.
through the achiral or the chiral molecules. Now the length of the sample tube is measured in decimeters. So you want to make sure your unit is in
تقاس
decimeters.
بالديسيمتر.
Now 1 decimeter is 10 millimeters. So those are some conversion factors that you're going to need to know when dealing with problems that ask you to calculate the specific rotation. Now the subscript of the specific rotation is the wavelength. And the wavelength, lambda, is in units of nanometers. The superscript is going to be the temperature in Celsius. Now sometimes you may see this. When you see that, what that means is that this is the sodium D line with a wavelength of 589 nanometers.
تحديد الطول الموجي
And this
للضوء
particular specific rotation is
ودرجة
calculated at a
الحرارة
temperature of
25
25
درجة
degrees
مئوية.
Celsius. So that's the formula that you need if you wish to calculate the specific rotation of a pure isomer.
يعني احنا ما نريد نحسب دوران النوعي، هي هاي الفورمولا اللي هي هاي الصيغة، ومبين عندنا التركيز وطول التوب، اللينث اوف توب، السبيسيفيك روتيشن، الابزرفد روتيشن اللي هي تقاس بالديجري، اللينث يقاس بالدي سي متر اللي يساوي لنا 10 سنتيمتر. تمام. يجب تحديد درجة الحرارة والويف لينث الخاص باللايت. هنا عندنا 589 نانومتر ودرجة الحرارة هي 25. فهاي طبعا هي المعادلة اللي تستخدم لحساب الدوران النوعي اللي هو specific rotation.
Or certain enantiomer. Now the next thing that we need to talk about is something known as enantiomeric excess. So this occurs when you have both isomers, let's say the R and the S isomer in solution, but they're unequal. One exists in a concentration that's more than the other. Enantiomeric excess can be calculated by taking the observed rotation of the solution or the sample and dividing it by the specific rotation of one of the pure enantiomers. And then you would multiply this by 100%. So if you have the observed rotation of the solution and the specific rotation of one of the enantiomers, then you can calculate the enantiomeric excess with those values. Another way in which you can calculate the enantiomeric excess is if you know the relative.
طلاب فقط اكو ملاحظة، احنا الانتايمرز في الطبيعة ممكن ان تأتي بشكل بيور واحد من المتمارئات، وممكن ان تجي بشكل خليط. الخليط الراسيمي ريسملك ميكستشر اذا كانت نسبة المتمارئات متساوية، يعني 50% مثلا من اس 50% من ار، فهنا inactive يعني optically inactive، يعني لا يدور مستوى الضوء المستقطب لا نحو اليمين ولا نحو اليسار، يكون واحد يلغي تأثير الآخر. وفي بعض الأحيان هذا المكستشر يأتي بنسب مختلفة، يعني الآر خلينا نقول 75% والأس 25%، فراح يدور مستوى الضوء المستقطب بشكل يعني جزئي أقل من البيور. فإحنا هنا انتايمر اكسس معناه نحسب نقدر نحسب من كل نوع إذا كان ار أو اس قد النسبة الموجودة في هذا الخليط.
Percentages of the R and the S isomer. For instance, let's say if a certain sample is 80% R and 20% S. The enantiomeric excess is the difference between the two. It's the absolute value of R minus S or S minus R. In this case, it's R minus S because this is bigger. So it's going to be 80% minus 20%. So we get an enantiomeric excess .
If you don't have a website for your business, it might as well be invisible.
Now the enantiomeric excess is equivalent to the optical purity, but in decimal form. So the optical purity is going to be 0.60, which is equivalent to 60%. Now another formula that will help you to calculate enantiomeric excess, particularly if you have a sample where R and S are, let's say, in grams or moles as opposed to a percentage, you could use this formula to calculate the enantiomeric excess. It's equal to the absolute value of R minus S or S minus R divided by the sum of the R and the S isomer times 100%. So using these values, let's say if we have 16 grams of R, 4 grams of S. If we were to subtract these two, we would get 12. We won't get 60%. Nevertheless, 16 is 80% of the total of 20. So as a percentage, these are still the same. But if we were to use this formula, we can still get 60%. So if we take 16 grams of the R isomer, subtracted by 4 grams of the S isomer, and divided by the total, 16 plus 4 is 20, we're going to get 16 minus 4, which is 12. 12 over 20 times 100%. 12 divided by 20 is 0.60 times 100%, which will give us 60%. So that's another way in which we can calculate.
إذن طلاب هنا احنا على مود نعرف نسبة كل متمارئ، فأما عن طريق الغرامات أو المولات أو عن طريق الابزورب روتيشن او عن طريق النسبة المئوية. تمام. فهذا هنا اعطانا مثال كيفية حساب النسبة المئوية لكل متمارئ. نعيد مرة أخرى، في معظم الأحيان هاي المتمارئة تجي على شكل بيور، وفي بعضها تجي على شكل خليط راسيمي. الخليط الراسيمي يعني معناها المتمارئين بنفس التركيز، لذلك تكون optically inactive. وفي بعض الأحيان النسب لكل متمارئ تختلف، ممكن حسابها.
The enantiomeric excess, if we know the relative amounts of RNS in units of, let's say, grams or moles. But if we're given a percentage, we can simply just subtract them directly, and that will give us the enantiomeric excess as a percentage as well. So now you know how to calculate the specific rotation, the enantiomeric excess, and even the optical purity. So now let's work on some practice problem. Number 1, 0.5 grams of a chiral stereoisomer was dissolved in 20 milliliters of solution. The observed rotation measured by a polarimeter was found to be -3 degrees at 25 degrees Celsius using a wavelength of 589 nanometers. The sample tube of the polarimeter is 20 centimeters long. What is the specific rotation of the stereoisomer? Well, let's begin by writing the formula.
هذا عندنا مثال حسابي 0.5 غرام 5 بالعشرة غرام من chiral isomer was dissolved in 20 milliliter of solution. تم إذابته 20 ملتر من المذيب. The observed rotation measured by a polarimeter اللي هي الدوران اللي تم observed rotation اللي تم قياسه من خلال هذا الجهاز اللي هو polarimeter was found to be -3 degrees اللي هو ناقص 3 degrees بدرجة حرارة 25 واستخدام طول موجي 589. The sample tube of the polarimeter is 20 centimeter long. الخلية المستخدمة طولها 20 سنتيمتر. What is the specific rotation؟ مطلوب في السؤال What is the specific rotation of the stereoisomers؟ مطلوب specific rotation الدوران النوعي. فهسه راح نحسب الدوران النوعي.
The specific rotation is going to be equal to the observed rotation divided by the path length times the concentration. Let's write down what we know. We know the observed rotation is -3 degrees. Now what about the path length, or the length of the sample tube? The length of the sample tube is 20 centimeters. Now we need to convert that to decimeters. Remember, 1 decimeter is equal to 10 centimeters. So if we divide 20 by 10, we get 2. So L is going to be 2 decimeters.
حولنا السنتيمتر إلى ديسيمتر.
Now we're also given the mass and the volume. So we can calculate the concentration in units of grams per milliliter. So if we take the mass of the chiral stereoisomer in grams, which is 0.5 grams, and divide it by the volume of the solution, which is 20 milliliters, this is going to be 0.5 divided by 20, giving us a concentration of 0.025 grams per milliliter. So right now we have everything that we need to calculate the specific rotation of the stereoisomer.
إذا طلاب أول شيء حولنا بالديسيمتر اللينث اوف سيل، كذلك حولنا التركيز بالجرام لكل مليلتر، وكل شيء هسه حاليا يعني موجود.
So let's go ahead and do that. So first, let's replace the wavelength with 589 nanometers, which corresponds to the wavelength of the sodium D line. So we could just put D for that. the temperature is 25 degrees Celsius, so that's going to be the superscript. And then alpha is -3 degrees. L is 2 decimeters. And the concentration, 0.025 grams per milliliter. 2 times 0.025, that's going to be 0.05. -3 divided by 0.05, that's -60. So the specific rotation of this stereoisomer is going to be -60 degrees. And that's the answer for this problem.
شكرا جزيلا. إلى هنا ينتهي الفيديو.